Lecture. Let's go.
Okay, great. Thank you, Rob. Okay, so we kind of went very quickly through a proof about if you exclude a tree and a complement of a tree last time. So what I'm going to do for the beginning of this time, so for the first maybe 15 minutes, 20 minutes, I'm going to kind of run back over the general strategy of that proof and present in hopefully a clear fashion. So just to kind of recap, so the theorem we're proving is that the class of graphs with no, let's say, T or complement of tree, so for every tree T, I think I said this with two forests before, but you can embed any pair of forests in a bigger tree. So I can just state this equivalently with just a single tree. So if we exclude the tree and a complement of the tree, then we get the strong Erdős-Hajnal property. Okay, and therefore also you get the Erdős-Hajnal property. Okay, so I'm going to just kind of talk through the general strategy of the proof. I hope I convinced you last time that there's quite a lot of detail to go into to kind of fill everything in, and also that you really don't want to know too much about what the constants are because there's lots of rounds of iterating Ramsey and things like that. Okay, so what's the general strategy? So the idea is you take a sequence of big boxes, so linear-sized boxes, and look for a rainbow copy of T. So look for a rainbow T. So we'll have some long sequence of boxes. So we start by defining some gigantic constants. You take that many boxes of linear size, and now we'll look for a rainbow copy of the tree. In other words, each vertex of the tree should be in a different box. Okay. So we start with our arbitrary sequence, but now we do some refinement. We do some shrinking. Maybe you throw away some boxes, so we'll drop to some small subset of the boxes. We'll shrink the boxes, all with the goal of making it a bit nicer. So we refine our sequence. To get two properties. So firstly, and I'll say this in opposite order from last time. So any ordered tree. So if I've got a rainbow tree, even if I've got a rainbow path, the vertices might bounce around and come in any given order, and I actually do need to track the order of the vertices. So I'm going to work with an ordered tree. So I've got a tree and an ordering on the vertices. So for example, there's 4-vertex path, ordered that way. Okay, so if I take any ordered tree on, at most, some constant number of vertices, so on a bounded number of vertices, so I'd like to say that either it occurs kind of very robustly, either it's sort of like some weed, it occurs absolutely everywhere and you kind of can't eradicate it anywhere, or it doesn't occur at all. So either doesn't occur at all, and by occur I mean as a rainbow copy, or for every subset of boxes, it occurs robustly. And what do I mean? So if this path of length 4 is going to occur robustly, then if I pick any sequence of 4 boxes, and okay, I'm not even going to keep the whole box, I'm going to just take a constant fraction of each box, then there will be a copy of the tree joining up those boxes. Okay, so it's kind of super robust, meaning that any 4 boxes, if I take them in order, I get a copy of the tree, even if I shrink the boxes by some big constant factor. Okay, so in other words, I can't get, this is a tree I can't get rid of. Okay, I can't get rid of by refining my sequence. Okay, how do we do it? Well, again, just sort of recapping what I said very, very fast, sort of towards the end last time. We start with our huge sequence. For each collection of 4 boxes, so it comes in 2 phases. So the first phase is we just get rid of anything we can. So I look at every collection of 4 boxes. If I can shrink them and get rid of so that there's no copies of the tree left, rainbow in the right order in those 4 boxes, I'll do it. So I kind of repeat, repeat, repeat. So everywhere I can, I get rid of the tree. And now it's the case that for any collection of 4 boxes, either it sits there robustly, I can't get rid of it, or I actually have already got rid of it. Okay, and now apply Ramsey, hypergraph Ramsey. So you drop to some log size subset, so some tiny subset of your boxes, but still a big constant. And now either every 4 boxes, you've got your tree robustly, or the tree's vanished entirely. There's no set of 4 boxes where you have it. Okay, so that's a kind of much nicer setup, because either we've got our tree everywhere, or we've got our tree nowhere. So this is, again, any given bounded size tree. We'll do this for all trees up to some reasonable size. Again, constant size. Okay, now, that's great, but what if I only get tiny trees? So what I want to be able to do is glue my trees together to build bigger trees. And to do that, okay, well, suppose I got some tree, for instance, this one, and I want to build some bigger ones. Okay, what am I going to do? Well, I don't know very much about individual vertices. So I want to show strong Erdős-Hajnal. I'm assuming that I can't find 2 linear size sets without edges between them. This gives me a kind of bulk property of vertices. If I have 2 big sets of vertices, 2 linear size sets, there must be an edge between them. Yeah.
Sorry, I don't quite understand the Ramsey argument. So for each 4 set here, you could say either it has the property or not.
Yeah.
And so you could apply Ramsey to that, and then I
Yep.
get a good one, or you get one where every 4 set, there exists a way of killing it.
No, so thank you. I actually do kill it. So if there exists a way of killing it...
Before you do Ramsey, just kill it.
Yeah. Yeah, so we eliminate the tree everywhere we can. Okay, and the thing you should worry about are the constants. So the constants have to change at every step. So the constants are floating.
Every 4 sets,
Yeah.
when there exists a bad set, you pass to that bad set.
Right.
By one.
Right. So if for every 4 set, I look at every 4 set, if I can shrink so that there's no copy of the tree between them, I will do the shrinking. And now the tree will never reappear. Once it's gone, it's gone.
So I'm maybe confused by in what order the shrinking is happening. So you have this huge set of boxes, and every 4 set
Right.
has one bad set. But those sets might be disjoint.
So one is iterative shrinking.
Okay, this is what I did.
Okay, so we say, is there a 4 set where I have a copy of the tree and I could get rid of all copies of the tree? So I look at a 4 set. If I can, so four boxes, if I could shrink them all and get rid of the tree entirely from those 4 boxes, I will do it. Great, I've killed the tree in one place. Okay, so I keep doing that.
Right, that first. And that's only a bounded number of steps because there's only a bounded number of boxes.
Right, so if I've got B boxes, then after B to the 4th iterations of this, every time I'm shrinking things by a constant factor, so you can see the constants are...
Every 4 set is either there robustly or it's...
Yes, yeah, yeah, yeah. Thank you, Rob. Okay, so again, we start with our collection of boxes, we go through a shrinking phase where we shrink everything in sight where we can get, if it enables us to get rid of occurrences of some tree on some set of boxes. We keep doing that. Eventually, we can't do any more shrinking. So for every set of boxes and each possible tree on those boxes, either the tree occurs robustly, it's sort of ineradicable, or we've actually got rid of it already. Okay, and now we apply Ramsey. In fact, we apply Ramsey for hypergraphs for every possible tree. So we'll kind of iterate lots of times. So clearly the numbers are not good. We iterate lots of times. And now we've got this nice sort of lots of Ramsey. Okay, well, it's the same thing done over and over again. So we do this lots and lots of times. And now we have this sort of nice clean setup where for each tree, either it occurs robustly everywhere or it doesn't occur at all. Okay, so that's sort of the first thing we need to do. But we also want to be able to glue these things together. So, we're going to have trees. Let's say, I'll assume okay, I mean, it goes like this, but it's complicated to keep drawing, so I'll just draw a line. So if I kind of think about any 4 boxes, I can start finding as many disjoint copies of the tree as possible. Well, this kind of robust occurrence means actually I can cover most of the vertices with these trees. Because if I look at what I haven't covered yet, let's assume these are all the same size, if there's still a constant fraction left, then there should be a tree spanning them. So I can get a huge matching of trees. Okay, so that's great. I'd like to glue this to something else.
So again, this is the tree that you're looking for at the end, or this is any one of these bounded?
This is any bounded size tree. This is a small tree. So I'm going to forget this tree that I'm looking for. I'm going to forget T for the moment. I'm going to inductively build up bigger and bigger trees.
But it could be that you could have the option that there are no occurrences of the tree, right?
Yes,
so
yeah.
For the collection of trees, some trees occur and some others don't.
Yes, yeah. So it might be there is no path of link 2 or something. That's in the increasing ordering. Right, so some trees occur, some trees don't. I'll just remark, one tree we know that does occur is K2. Why does K2 occur? Well, otherwise we've found a pair of, think about any 2 boxes. They still have linear size, not as big linear as it was, but still linear size. And either we have 2 linear size sets that are anti-complete, or there's an edge between them. Okay, and if there's an edge between them, we have our K2. But if we haven't got rid of the K2, actually I get a nice big matching as well. Okay, so at the moment I don't know what's left. There may only be tiny, tiny trees left. Okay. Right, and then the other thing we want is that, I've got some tree I can get all over the place. Maybe it's a very small tree. I want to be able to kind of inductively somehow to build up and to grow bigger trees. So I need to be able to grow little trees together to make big trees. And the sorts of trees I'm going to grow, so I can start with a star and then glue a bunch of stars together. Actually, I should draw this. I'll do the same drawing, but from the top rather than the bottom. So I start with a star. If I can get a bunch of stars and glue them together, that's great. I've got a depth 2. Now I kind of iterate, grow a bunch of these things together, and I'll get sort of bigger and bigger trees. So that's my goal, is to build trees like that. So I need a way to glue things together. What's bad here? Well, I'd like to glue things. I'd like to control where I glue. I'd like to control where edges appear. So what I'd like is sort of be able to glue things to the ends, sort of left and right ends, and not be forced to glue in the middle. Okay, so what I'd like to say is that if I sort of take collections of blocks, the edges tend to appear at the end, joining the ends before edges appear in the middle. Okay, so intervals of blocks Okay, I'm going to be very vague with this. I'm just going to say they're preferentially joined at the end. So if I take kind of 2 collections of blocks and start looking at, start building up taking some vertices, then I'll tend to find edges joining the end, so they're more densely joined at the ends than they are in the middle. Okay, now this was the argument with patterns from last time. I'm not going to go back through that. But but I'll maybe just say, what was the kind of key idea? Well, if I've got some collection of blocks, here's another block. Suppose I start taking vertices out of this sort of left-hand block and look at where they're joined to these right-hand blocks. Okay, so I'm going to just start growing a small set here. Remember, the convention is that this might be quite small, it's not necessarily linear. I'll grow until I see a linear fraction of one of these blocks on the right. So I'd like to see a big piece of one of these blocks. Okay, and suppose it's the case that it's actually this block I see a big piece of, and since I'm just going to stop as soon as I see a big piece somewhere, I know that I miss a big piece. I might see some of these other blocks, but I'll miss a big piece of each of those others. Now, that's looking quite interesting. This has happened. Suppose I could guarantee this would happen. Suppose I could guarantee and I could choose where I landed in the middle of this sequence. Okay, well then, I do the following. I take this, and I'll draw it above, and I'll shrink to the neighbors of, so this set A, I'll shrink to the neighbors of A and the non-neighbors of A in the other blocks. Okay, and now I've got, so this was sort of B1 to B4, now it's B1 prime to B4 prime. So if this happens, then I'm in good shape. Well, at least I've got one step where I've generated some private neighbors for this block. So I've got a set that covers this second block and doesn't see anything in the other blocks after I did my shrinking to clean things up. Okay. And now I'm going to try and do the same thing again. So I'm going to, again, I'd like to find an earlier block. I'd like to find a piece of the earlier block. And now I'd like to see maybe a big piece of B1, or now B1 prime. So what I'd like is that I see a big piece of this and miss a big piece of those. Okay, and again, if I can do that, so I'll pull this, I'll shrink to the neighbors in B1, non-neighbors in the other sets, and I will pull out some private neighbors for B3 double prime. Okay, so kind of keep going. Okay, I mean, it's both a question of can I do this, but let's suppose just for a minute I can keep doing it. Some earlier block.
I see.
So I've just got some box earlier on, and I'm just saying, suppose there's an earlier box, and I can take some stuff out of this earlier box, cover a big piece of B1 prime, and miss a big piece of the others.
And you're also missing wherever you took the A from.
Oh, I don't care about A, so so quite happy to have neighbors in A. I don't worry about that. Here's good question. Here's what happens if I can do this 4 times. Suppose I can keep doing this. So I've got B1. Okay, I'm losing track of how many primes I need, so I'll just write star. I've got B1 star up to B4 star. Above each of these, I'm drawing something that covers it, but is non-adjacent to the other blocks. And you're quite right, there might be edges between these. Fine, I don't mind. But now I'm in good shape for my inductive effort. So if I've got a tree on these 4 blocks, then I can add a leaf, just one leaf because things above might be adjacent to each other. But I've got my, I take a copy of my path, I'll draw in orange maybe. Okay, maybe I'd like to add something to the second vertex. I can just take a neighbor up there, and I know. So this gives us a way to grow a tree by one vertex. Okay, so if I have a big matching one, then I'm sort of happy. And I'm happy to go by induction because, okay, I've got a matching covering some nice big set of blocks. So now I will start the process again with those blocks. And now the tree I actually need to end up with is one vertex smaller. Okay, so that can't happen too many times. Okay, so I kind of restart, everything's much smaller, but I can do the same process again.
So all this works because you have a maximum degree of little silent n.
Yes, yes. And again, that's another reason that the constants are not good, because that epsilon is spectacularly tiny, and Erdős has spectacularly bad constants. Okay, right. So if we can get this thing of being able to cover any box and miss any others, then we get matchings, and that's good for us. Okay, and again, this has to happen robustly because we take this first set, things shrink down. I need to be able to do it again from somewhere. Okay, so if we can kind of parachute in and see any box and miss the others, fantastic. Right, so this was all the argument day before yesterday with patterns. So the goal of that, and I'm not going to drag you through the argument again, but the goal of that was to say, okay, after some refinement, we can ensure that either this happens very robustly, so that will be this outcome, so I can just keep doing this, or it doesn't happen at all. Okay, so it's never the case that given 4 blocks or given a sequence of blocks, I can cover a big piece from the middle without covering the ends. Okay, so it says that I'll always actually, so the key thing will be that as I cover these blocks, I'll cover either the left-hand end or the right-hand end. Okay, so there's a lot of work hidden in there, but basically the idea is you think about middle versus ends, and you kind of do some grouping up to amplify that. So I'm skating over lots of things there, but you can arrange it so that if this doesn't happen, then as I grow, I'll cover almost all of the first block or the last block before I cover anything in the middle. So it's a sort of convexity type thing that you cover the ends before you cover the middle. Okay. Right. Okay, so these are the sort of 2 general properties we need. And I've been purposely a little bit vague with this intervals blocks are preferentially joined at the ends, but that's essentially what it's saying, that if I start growing, I'll see the ends before I see anything in the middle. Okay. Maybe this picture can go. Right. And then with all this sort of preparatory work and all this kind of cleaning up of structure, I mean, this is very much kind of standard type of technique. You have some big, ugly problem, and you're trying to kind of refine and make it nicer and nicer, so you drop to smaller and smaller subsets. Your world is getting nicer and nicer, less messy as it goes, and then you can do something in that cleaner world. Well, okay, I mean, these are kind of, this is a sort of slightly rougher structural thing. This is very, this is nice. This is sort of saying something about bulk behavior of sets of vertices. Okay, what are we going to do? So, kind of main argument, after all that, we ask, okay, what can I grow? Well, now we're dealing with ordered structures. We want to join things at the ends. So we want our trees to be rooted at the left-hand end or the right-hand end. So grow left or right rooted trees. I'm not sure whether to put a hyphen there or not. Okay. Right. So there'll be sort of some tree I'm growing, kind of TL. There'll be a left-rooted tree, and let me draw it so they look different. And maybe TR will be a right-rooted tree. Okay, and the trees I'm thinking of again are going to be, they're going to be fast branching trees of some particular depth, and what I really care about is the depth. Okay, so I'm going to, it's going to be the depth that is the thing you have to work to get rather than the branching factor. Okay, but just branching fast enough that, well, some constant rate. Okay. Right. So here's what you do. You say, okay, I'll take a bunch of copies of TL. Here we are. So I'll sort of take a big matching of copies of TL and a big matching of copies of TR. And I'll just sort of, on some sequence of blocks. Any set of blocks is fine. So say some interval of blocks, say. Okay. And that's going to be my basic...
You've shown in the argument that these two are good ones, or the difficult ones.
Right, so this is going to be inductive argument, and we start with kind of... Start with K1. Yeah, thank you. So now let's think about the inductive step. So I've managed to grow some tree TL and some tree TR. TL rooted at the left, TR rooted at the right. And the thing is, I'm going to be happy if either TL or TR gets big. It's not always I'm going to get the same size of tree in both directions. It might be there's something structural that means that it's much easier to get trees left-rooted than it is to get trees right-rooted. Fine. Yeah.
Sorry, I just realized, yes, so you just need to find one copy of this, and then the property tells you, then you have many.
Yes, exactly. Right. So the inductive step's going to be, suppose I've got a TL and a TR that I've grown. Okay. So I know that since I have one copy left-rooted of TL, one copy right-rooted of TR, I can get copies absolutely everywhere. So I'll pick an interval, and then I'll find lots of disjoint copies of TL, and by this sort of robustness property, I know that I'm going to get lots of copies. So kind of near to a matching. So this was by the board that I've half rubbed out. And similarly for TR, I'll grow lots of copies. Okay, and all I really care about is that the TLs are rooted in the left box, and the TRs are rooted in the right box. Okay. Okay, so now we take a couple of these. Right, and these are going to join, tend to join at the ends before they join in the middle. Okay, so you need to do this a bit carefully. And I haven't said too precisely what this business is. But you can arrange it so that, in some sense, the first edges you get are edges that join either the left ends, the right ends, the middles, or the outsides. So the kind of first edges that appear join kind of the ends one way or the other. Okay. And that's going to be using this property and some random selection. So there's a bit of work to do in there, which I will not tell you about. But it's not very hard. It's just you have to do it the right way around. Okay. So let's say the first edge you get is that. Okay, joining the two left-hand ends. So here was a copy of TL. Here was another copy of TL. I have to be sure there's no edges between them, but by my first edges appearing, okay, maybe let me say it more carefully. So actually what we'll do is we'll take copies of these, we'll take them in a random order, and it's very likely that kind of the first edge that we hit joins the ends of a pair that are not joined in the middle. Okay, and simply because simply for reasons of density, actually. So, okay. So, again, I'm not going through that argument. I'm just saying you can do it using these, using this sort of property.
Sorry, I was going to ask whether you answered. The first means there's many matching of trees. You order them randomly, say,
Yeah.
and then look rates between them.
Yes, exactly, yeah. Good. What does this give us? So this gives us a copy of TL, and then joined to another copy of TL. Okay, great. That's a bit better. But if I can do that, I could have made, I get this graph once, this tree once, so I can get it lots of times. It occurs, so it occurs robustly. So again, either it doesn't occur at all or it occurs absolutely everywhere. It occurs absolutely everywhere. So let's sort of call this TL prime, since I can think of it as left-rooted again. So now I'll sort of do the same thing again, but rather than TL and TR, I'll do it with TL prime and TR. I'll take two of these. Again, if I get this joining happening, well, now I get an additional copy of TL. So this gives us, okay, two copies of TL join, and now we repeat and get lots of copies of TL joined at a root. Now we've gone one deeper. Okay, so we're sort of happy if that happens. Okay, this is if they join at the left. Okay, so if we can keep joining things at the left, so actually, when you say it more carefully, you actually kind of induct on how many of these branches you have as well. But if you can keep joining things on the left, you keep adding copies of TL joined to the root.
So, sorry, this picture is, so you've taken TL prime, repeated the argument, so you've got an edge between two copies of TL prime. Is that what
Yes, yeah. So
to me, it doesn't look like that. The picture doesn't.
yeah, so secretly there's another copy there sitting.
Two copies of TL prime and then an edge between the roots. That's what we've got.
Right, so here's one copy of TL prime. Here's another copy of TL prime. And I'm happy to forget this bit, so this is the bit I'm after.
Yeah, so I think it would be quite easy if you draw it on the line above next to TL prime. Two copies of TL prime. And then, sorry, doing this then gives you, I see, you have lots of copies of TL prime all joined.
Right, so it gives you, so again, just you get TL prime joined to TL prime, but that contains, actually,
These two, I see, and you just ignore that.
so inside this I've got,
I see.
this is what I really care about. I'd like to glue lots of copies of TL at the root. Yeah. And each time I do this, I'll get another copy of TL, plus some other stuff that I'll ignore, because I'm only tracking copies of TL. Okay.
I'm sorry, could you say it again? So what is this business of the order of the edges that so you say maybe the first edge comes this way or the edge? I didn't get that.
Right. So I'm claiming but not showing, because I want to skip the argument that we can arrange it so that there's sort of some line here and some line here, where the only edge between them joins, so there's only one edge between them and it joins one end to the other end, left or right to left or right. So arrange, or you can find two copies, so like so and like so TL, TR, TL, TR. such that only edge between them joins the ends. So so you can, by this sort of random choice and careful tracking of bulk behavior, extract that. So you can prove that. And I'm saying if it happens that things go on the left, and let's assume it always happens the same way. I mean, you can mix it as well. If things always happen on the left, then you can iterate and build up this bigger and bigger tree. Okay. Everyone happy-ish so far? Okay. If it happens on the right, same argument, just reflected. So, yeah, I'm going to hold up a mirror and change L to R. But it might be you have sort of left joined to right. So let me get this the right way around. So suppose I have left joined to right. Okay, well, actually that's good. So when I've drawn it, TL is much bigger than TR. So this vertex on the right here, it's quids in. It's a happy vertex because it's not just got a copy of TR, it's got a copy of TL. I mean, spun around, but it's got this great big tree hanging off it now, rather than just TR. So a vertex on the right is happy with TR if it gets TR, or I mean if it gets TR like that. So kind of that would be good. But this is just as good because TL is at least as big as TR, and you can do the same argument again. Okay, and then there's one awkward case. So
sorry, so we just said you can grow either of them. You don't mind which one to grow.
Yes, yeah. Right, I just want to grow a tree that is, well, what is TR's ambition? Well, so the right-hand side ambition is to grow something like that. Lots of copies of TR tied together at a root, hanging off a root. Okay, if it accidentally gets TL, so the orientation is spun round, but TL is at least as big as TR. And again, this is why I'm growing a branching tree rather than growing an arbitrary funny tree that might be spindly or whatever. Any tree as long as it branches and has some reasonable depth. So TL is at least as big as TR, so this is just as good as TR. Okay, so if I grow a bunch of copies of TL, brilliant, I'm happy.
Your aim is just to grow one of them by one level.
Yeah, yeah.
And sorry, so it might be that these things all sticks the whole time, and then you do
Fine,
stuff
yeah,
around and
yeah.
in a second.
So actually, if you do it more, if you do it more carefully, you track. You say, okay, I can grow TL with some number of copies of TL hanging off it, and TR with some number of copies of TR or TL hanging off it, and I try and get one more on either side. So that simplicity, let's just assume it all happens on one side. Okay, and then there's one awkward case. So TL is sort of, okay, on the left we're really ambitious, but the sort of annoying thing that could happen, the risk of making this picture even more confusing, I'll put in an edge like that. Okay, and I have a vertex at the left, and it's hoping to get a copy of TL here, this sort of huge TL, and it's going to stack them up. Oh, and it only kind of gets a tiny little TR. Okay, so I'll just say you can get around that. You have to do a little bit of maneuvering to find the thing you want, but there's another argument that gets you around that. So, and it's not, yeah, you just need a little trick to look at how things attach to each other. So again, I'll skip that, but I'll just say, kind of full disclosure, there's something you have to do. Good. Okay, any questions before I move on to this? Okay, well that was that was a quick 40-minute recap. What am I going to do today? Okay, so I told you back on Monday that here's a list of graphs we can do. So there was kind of cliques, there was P4, there was the bull, and there were these two closure properties as well. So complementation and substitution. So the Allen-Pax-Olomarchi result on substitution. And for quite a long time, actually, that's all that was known. And more recently, there's been some further progress. And so it's known for some more H. Still only a kind of small family of H, but more than there were. So my plan today, I'll tell you about one of those results. And then tomorrow, I will kind of bring you up to date in terms of, OK, here's a list of what we know. And then I'm going to talk about another result tomorrow. So my plan today, if I can, I will try and get through the proof for C5. And then tomorrow, I'll talk about VC dimension. OK, so this is again with Maria Janowski, Paul Seymour, and Sophie Sperkel. So I think 23, but that's plus or minus 1. So Erdős-Hajnal holds. So when H is equal to C5. OK. We were really happy to get this one because it was like a particularly annoying example. And it's also one of the examples that gets sort of talked about in the original papers on this as a sort of a good test case. So, OK, so let me tell you about this. OK, well, before I tell you about the proof, I want to tell you there's two tools, two useful tools I want to talk about. So, two useful tools. OK, so another variant on, we have the Erdős-Hajnal property, we have the strong Erdős-Hajnal property, and we have the quasi-Erdős-Hajnal property. So let's just remember the strong Erdős-Hajnal property. So that said, I had two sets of size at least constant n, and either they're complete or they're anti-complete. They have all edges or no edges. And there's a simple recurrence. Actually, Yuval implicitly used exactly the same fact in his talk. So his exponent, was it log 2 or 3, came from this sort of recurrence. So this gives the Erdős-Hajnal property. So the sort of linear complete or anti-complete pairs gives you a polynomial cograph and therefore clique or independent set at the end. OK. So here's a nice observation that István Tomon made. Which I'll write his. Now I have to get the accents, I think that. Can anyone correct me if I'm wrong? So the A.
The A of István, I think not in his last name.
Okay. Maybe. OK, so OK. OK. Suppose I could get a larger, more than 2. I mean, this was bipartite. What about multipartite? So I'd like it either to be complete or anti-complete. OK. So if I could get more of them, well, maybe they wouldn't need to be quite so large. OK, so this is the idea. Or I'll get to the idea in a second. And you can think, well, how large do I need them to be? And you have some trade-off between how many you get and what size you need in order to get Erdős-Hajnal out at the end. OK, so here, you do need to be linear to get Erdős-Hajnal out. If I told you I had some number here, how many would I need? Okay, so you can you can work out what sort of thing you need. But even better, if I got the right trade-off, I don't need to decide in advance how many I have. So I'd be happy with either 2 that are linear, or 3 that are, well, linear but with a slightly less good constant, or 4 that are linear but with an even worse constant, or log n that are linear, sorry, log n that are, well, n over polylog size. So
And do you go for a cograph or?
just complete or anti-complete. So not a cograph. Every pair complete or every pair anti-complete.
But the aim is to get some cographs and then later on use that to have.
Yes, yes, yeah. So exactly the same as here. You run it all the way down. You get a big. Well, you can either do a one-step induction, or you can just run it all the way down. You get to generate a cograph and extract. Okay, so let me just say that more carefully and with numbers. So we say that a hereditary class. I'm going to try and spell G correctly. There we are. G has the quasi-Erdős-Hajnal property. If it exists C and K positive, such that for every G and G, there are, okay, I'll say what T is in a second, but for the moment T is just some number. So T is at these 2 sets. A1 up to AT contained in the vertex set of G, such that. Okay, so we want 2 properties. We want A1 up to AT, pairwise disjoint, and size at least all right, n for the size of G, n over T to the K, and I'll put a constant C there as well. So you can ignore the constant C if you want, but essentially n over T to the K. And then either AI, AJ complete for all I not equal to J, or AI, AJ anti-complete for all I not equal to J. Okay. And I haven't said what T is, so let me say what T is. It's whatever you want. For some T. Shall be T sets for some T at least 2. That's not proper English. Okay, right. Okay, so it says I can find, for some T, so think of, I mean, this C times n over T to the K, it's just n over some polynomial in T, n over poly T. So I've written that out formally, but then let me say informally. So T sets of size n over poly T is the way to think about it. Okay, and then either it's all complete or it's all anti-complete. And it's not hard to show that quasi-Erdős-Hajnal implies Erdős-Hajnal. Okay. So why? So again, you make the cograph argument. So I'll just sort of gesture at it. We've got some T, we don't know what it is. And this collection is either complete or anti-complete. But inside each of these sets, we can find, so here, we've got some graph G, we extract what quasi-Erdős-Hajnal tells us. Inside each piece, where we've got size, sort of, I'll ignore the C, n over t to the k. And so whatever we can get, that's what we get as the size of our cograph. And how many of them we have, we have t of them. Okay, so when we kind of do a recurrence, so we'll take these small ones, we'll put them together, they're all complete, all anti-complete to each other, so we still get a cograph. We put the smaller cographs together to get a bigger cograph. And we're okay as long as this is at least whatever our f of t is. Okay, now if f is a polynomial of small degree, well, you'll get your n to the epsilon from the top. You'll get t to the k becomes t to the k epsilon. So as long as epsilon is nice and small, that'll get outweighed by the t in the recurrence. Okay, so kind of check that if you have a small degree polynomial, then this recurrence is satisfied. So we can take f of n as n to the epsilon. That's our target. Yeah.
The same argument works instead of complete or empty, you have below the cograph.
Yes. Yeah. Maybe it's worth remarking. You might hope that actually a blow up of any graph would work. So here's a sort of naive way. Maybe we can get a big blow up of something, and then apply, try and argue by induction, apply Erdős-Hajnal, the inductive statement twice, once for the big graph, so to get a kind of complete, so something that looks like this or something that looks like this. So lots of these sets complete or anti-complete. So, I mean, let's say we have kind of A sets of size B, where AB is not too far off N. Okay, and you can try and apply induction on the A sets here to get A to the epsilon of them that are pairwise complete. And then inside each of these, you find a set that's, well, so you have a cograph structure. And then inside here, each of them, you find a set of size B to the epsilon that's a cograph. And you put them together and get a big cograph. Okay, that's a good strategy, but typically you've thrown some stuff away in the process. So when you find you don't start with your whole graph being a blow-up, you get something that looks quite like a blow-up. So maybe you have to throw away half your graph. And you also have problems that usually you don't get precisely a blow-up. You get something that's kind of a noisy version of a blow-up. And there's this leakage all the way through. So you actually drift off Erdős-Hajnal as you go. Okay, so you kind of need to really work hard to make that sort of strategy go anywhere. Okay, but this is in the nice world when we get complete or anti-complete of controllable size. Okay, so this is sort of really good news when this happens. Okay.
So in this case, you can see forward, it is a cograph, so you would actually just get exactly this. Okay, so now
okay, good. Okay, and again, let me kind of emphasize here. In order for this quasi-Erdős-Hajnal to work, we don't need to know in advance what T is. So we don't mind what T is. We don't need any advance information about what it's going to turn out to be. Okay. Okay, second tool. Combs. So what's a nice structure to get? And it's going to turn out, here's a very useful structure. I'll draw a picture and then define it. So what I'd like are some vertices A1 up to, let's say, AT and B1, sets B1 up to BT. So what I'd like is that AI, so BI is contained in the neighborhood of AI, but there's no cross edges. Okay. I'm quite happy for edges between the B's. I'm quite happy for edges between the A's for the moment. But this sort of bipartite structure looks like that. Okay, so this is going to be called a comb. So let me kind of just write down a definition. So an LW comb. So it's just going to be, so length and width. L is going to be the number of sets, and W is going to be how big these sets at the bottom are. So generally, I want my comb to be long, and I'd like the sets at the bottom to be big. Okay, so there's a sequence A1, B1 up to AL, BL, such that BI is contained in the neighborhood of AI for all I, and Bj intersect the neighborhood of AI is empty whenever I and j are distinct. Okay, so it's sort of a nice setup. And then there's a nice result that's going to tell us we can get combs.
Sorry,
Yeah. Oh, sorry, thank you. Such that and BI is at least W for that. Okay. Okay. Okay, so I want a lemma that tells us that we can find combs. And generally, combs for us are going to be a really good thing to have. So let me tell you about the lemma and the proof, and then I will start indicating why combs are useful to us. But I'll just point out they're a nice, simple structure. And whenever we can find a nice, simple structure, especially if we can find a large one, we should celebrate because maybe we can do something with it. We can add it to our set of ingredients. Okay. Maybe I'll also say, so this comb lemma, so we proved it in the C5 paper. There's actually, so the kind of the original idea of these sort of covering lemmas, again, also comes from Istvan Tomon. So another nice idea. We needed something rather stronger. So there's sort of a version of his, and János Pach, and then we needed to prove a stronger version to work for the C5 paper. But in spirit, it's sort of same type of thing. Okay, so just so I can write quickly, I'm going to cheat. Okay, so I want k to be bigger than 1, and sets, so I don't forget anything. Disjoint sets. Okay, let me write it down, then I'll kind of say what's going on. So, so for all x in A, the number of neighbors of x in B is at most some number delta. Then for any n, one or two things happens. So either there exists a T n over T to the K comb with centers in A. So by the centers, I mean these vertices A1 up to AT. So a kind of comb that points downwards, hangs downwards. Or, so the other outcome is that so So the portion of B that A can see is not too big, so it's at most some constant that depends on K, n to the 1 over K delta to the 1 minus 1 over K. Okay, so what's this saying? Either we get a big comb, we like big combs, or A has poor expansion. So this says we don't see too many vertices on the other side. Okay, so the way, I mean, this particular, you know, these are just the numbers that come out, or the expression that comes out. But the way to think about it is either we get a large comb, or our set A has poor expansion to B.
Here, the center is just the AX, right?
Yeah, so
N is the size of V here?
sorry?
N is the size of V?
Nope, n is just anything.
Oh, okay.
B can be infinite. Okay. Right. The reason I've written it like that is we were applying this over and over again inside a big graph G with n vertices, and then we'll always be moving down to some small subset, and we'll have thrown some of the graph away. And yeah. So n, I want to keep n as a global number. Okay.
So the first one is true for small values of n, and then suddenly at some point n, the second one becomes true. So you get overlap. The first one is
Yes,
more
yeah,
difficult, I guess,
yeah,
because everything-
yeah. Although in the application, it's going to be that this is an immediate win because this will give us strong Erdős-Hajnal. Sorry, this will give us the sets for quasi Erdős-Hajnal. Okay, maybe I'll say why it's going to be useful. So. Okay, so suppose I have a big comb. Okay, and again, this is going to be with n and t, and this is nice and polynomial size as we want it to be. So, these sort of n over t to the k, t of them, if I could arrange that these sets A1, so these A sets were pairwise complete or pairwise anti-complete, then I'd be happy. So our goal is going to be to do the following. I'll look at a comb, I'll actually find a comb that looks like this. So I'll have a kind of a vertex at the top that sees everything, that sees all the centers, and nothing at the bottom. And the second thing I want to arrange, so it's, you know, we're going to ask a lot, but the second thing I want is that this set is independent. Okay. Actually, maybe a question for the audience. Why would this be a good thing? So I've got t sets of size n over t to the k, and I'm assuming I don't have a C5. What does this tell me about the edges between the sets AI and? Right, so if I have an edge joining two of them, then I get a induced copy of C5. Okay, so if I could arrange this, then very nicely my sets would be anti-complete, and then I'd have the condition I need for quasi Erdős-Hajnal. So this is sort of the reason that, or one reason that combs will be good. There's going to be a few, actually looking at the time, I think what I'll do is I will get through the proof of the comb lemma, because I think it's a nice proof. I will do the application next time, and then try to get through the proof of VC dimension. But none of you have early flights, I hope. Okay, so let's just note what the comb lemma does and doesn't give us. So if the comb lemma gives us a comb, rather than poor expansion, then I'll get something like this, and hopefully, if I've done it right, A will be in the neighborhood of some vertex, and B will be the rest of the graph. That'll be great. I'd like to apply some inductive statement to get a big set here, complete or independent. If I get complete, I'm in trouble. So I'm going to have to work to make sure I don't get a complete set here in the inductive statement. I'll need it to be an independent set. And if I get that, so if I can manage to do all those things, then I'm at the finish line because I've got my quasi-Erdős-Hajnal. Okay, so that's why we're doing this. I'll say that the comb lemma is useful in several places, but this is the use for C5. Okay. Right, so that's sort of a picture from the future. Okay, I'm thinking about various books where pictures appear from the future. But anyway, if any of you like William Gibson, then there's one I'm particularly thinking about, Agency. Okay, so we're back now improving the comb lemma. So we want to show either you've got a big comb or you have poor expansion. Okay, so here's the idea. Let's run through A and generate a covering of B or whatever bits of B we see, and let's do it greedily. So let's generate or choose a greedy covering of neighborhood of A. So let's say A1, A2, ... where, okay, how do we choose the ordering? So each AI has as many new neighbors as possible. Okay, so each vertex that we add, we pick a vertex that sees as much new stuff as possible. Okay, so what does the picture look like? So, I mean, it looks a little bit like a comb. Well, except not quite, because these A's could have neighbors among the neighborhoods of earlier vertices. So let's say, let's write C1, C2, C3 for the new neighbors. Okay, so I'm going to work with ranges here. But before doing that, let's just sort of fix some range. So I'm going to think about just some number d, anything between, let's say, 1 up to n. And I want to think about how many of these sets Ci can have size about d. Okay, so how many AI Ci can have size in, let's say, 2/3 d up to d. Should we do it the other way around? So it works at the bottom. There we are. Okay, so we've got a roughly d. How many can we have? Okay, so let's do a little bit of relabeling. Say here are the ones. So let's say it's x1 up to xs, and these sets are y1 up to ys. And again, we have neighbors down to the left. Okay. Right, and we know that y1 is bigger than y2 and and so on. This was because we chose them greedily, so we maximized the number of new neighbors each time. Okay. Right, now if we look at any xi, I mean, we've got all these, I mean, the problem of these earlier neighbors, these edges to earlier neighborhoods, we don't have too many of them. So suppose, right, so each xi has at most d over 3 edges to union over j less than I yi. So the number of kind of down and left edges from any of the x's is at most d over 3. Why? Well, otherwise we could have taken it instead of x1. Okay, so if xs has, so ys has a size at least 2d over 3, and, or actually greater than 2d over 3, and if we have more than d over 3 down and left edges just in this range, then, okay, I'll just take xs instead of x1, and I've got more than d neighbors. So it would have been a better choice than x1. Okay, so we're inside the interval up to d here. Okay, it might have neighbors to things that we've forgotten that came earlier in the process, but I'm just looking in this range. Okay, good. So the xi's don't have too many kind of down and left edges. So the total number of down and left edges is at most s times this. Okay, so at most s d over 3 vertices in union of the yi have, are adjacent to later xi. Okay, so sort of in each block, there's going to be some that have some neighbors up and right. By the way, you don't have any, there are no up and left edges because each of these xi's, we grab all their neighbors when we introduce them. So it's only these up and right edges we have to worry about, and that we want to get rid of. Okay. Right. Good. So we've got at most this many vertices in the bottom. With neighbors up and right. Let's get rid of all the xi's with, I mean, what I'd like is, I'm trying to generate a nice big cone. So what's not good for me if I have a vertex here and most of its neighbors actually are seen by later x's. So let's discard all xi with actually, so I should maybe say, we've got at most SD over 3 vertices that are adjacent to later xi. The total number of vertices in the yi is at least, so size of union of yi is at least, okay, well, it's at least 2/3 d times s. Okay, which is twice this. So let's just keep the vertices that aren't covered by later x's. So it's just going to be a counting argument now. So at least d over 3, so at least sd over 3 vertices in the union of the yi are, I'll just call them private neighbors. So they're seen by their own xi and not by any other x's. Okay. Right. So we've got at least, on average, d over 3 private neighbors per set. And now it's just sort of the usual type of cleaning. So let's just throw away any x's that have very few private neighbors. So discard all xi with less than d over 6 private neighbors. Okay, I don't particularly care what the constants are. If 6 were 9, I wouldn't mind here. So we lose at most, okay? Well, altogether, they had at most SD over 6 private neighbors. It seems I'm also strong. Neighbors. So at least SD over 6 remain. And so at least SD over 6 over D, which is S over 6 of the xi remain. Okay, so what have we got? We've got some x's, we've got at least, each one has at least D over 6 private neighbors. And the total number is at least S over 6. Okay, so I mean, this argument, once you've gone to this point and you've realized that, so kind of the clever thing somehow is spotting that, and this was Isher and Tomlin's argument, spotting that vertices here don't have too many neighbors down on the left, and now you can do some counting. So this bit of cleaning argument, there's nothing very difficult. It's just you kind of have to spot at this point that you have this nice property, and then you run through the calculations. Okay. So this gives us a comb. So it's an S over 6, D over 6 comb. Okay, now, I haven't said what D is. D is just some number between 1 and n. So we're done if. Okay, so what we were looking for was a T, oh good, I've got it written over here, a T n over T to the K comb. Okay, so when is S big enough? So we're done if S over 6 is, sorry, let's write it the other way. If D over 6 is bigger than n over S over 6 to the K. Okay, so just that's a big enough comb, i.e., if S is bigger than some constant times D to the 1 over K, n to the 1 over K. Okay, so rearranging, it says D times n to the 1 over K. I'll just leave those conditions at the bottom. Okay, we're almost done. Right. Now we'll just break into ranges. So and sum. So we've got, so the ranges are going to be, so 2/3 delta up to delta, 2/3 squared delta up to 2/3 delta, and so on down till we get to constant. Okay, so just powers of 2/3. Okay, and then, so if we don't get a comb, then, okay, so our D is, so we're going to say D is going to be sort of some 2/3 to the I times delta, where I is at least 0. Okay, so those are the values of D we're taking. Then what's the size of A? Okay, so it's the sum of sum over, okay, sum over the, I'll write it slightly illegally, but sum over the different values of D that we're taking of, okay, so D, that was the number of neighbors that each xi saw, and S was at most ck wait, this is not correct. Let me rewrite this. If I can do base, it's n over d. So 1 over k. There we are. That's a bit better. Okay, so n over d is 1 over k, which is the sum over d of ck n to the 1 over k d to the 1 minus 1 over k. Right, and that's at most, I mean, this is just a geometric progression, and the first term is the biggest. That's when d is equal to delta. So it's going to be some constant times n to the 1 over k delta to the 1 minus 1 over k. Okay. Good. Okay, so that's the covering lemma. Yeah, you can, if you want, when you're applying it, you can tune k here. So you know, k can be whatever you want. Actually, well, just k equals 2 is enough in the application. But good. Maybe it's a good day to finish on time. So tomorrow I'll actually show the application to C5, and then I'll start talking about the more recent things.